Let's wrap up our exploration of digital signals and logic. So far, we've explored digital versus analog signals, different base systems, and logic gates. Now let's explore the core concept of this lesson, digital logic circuits. Now that we understand basic logic gates, we can explore more complex logic circuits composed of these logic gates. Here's an example logic circuit composed of 3 logic gates, the gates being a NAND, a NOR, and an AND gate. The circuit has 2 inputs, A and B, and 1 output, Z. To construct the truth table for this circuit, it's often beneficial to evaluate intermediate signals. So for this circuit, let's take a look at O1 and O2. Constructing the truth table for our circuit then, we'll need to account for our inputs, A and B, our intermediate signals, O1 and O2, and our output, Z. Given we have 2 inputs, that results in 2 to the 2, or 4 possible combinations of inputs, 0, 0, 0, 1, 1, 0, and 1, 1. The intermediate signal O1 is subject to a NAND functionality, so our signals at O1 will look like 1, 1, 1, 0. The signals at O2 are subject to a NOR functionality, so our intermediate signal O2 will look like 1, 0, 0, 0. And our output is subject to an AND logic gate, so our output at Z will look like 1, 0, 0, 0. And so this then is our final truth table for this logic circuit, where exploring these intermediate signals, O1 and O2, are helpful in digesting the performance of the circuit when you're just starting to learn how to evaluate these logic circuits. Let's build a digital comparator, where we want to compare 2 digital or binary inputs. So let's consider a black box then, subject to 2 inputs, A and B. We'll have 1 output, Z. The goal here then is that we want Z equal to 1 if A equals B, and Z equal to 0 if A is not equal to B. To accomplish this then, let's construct the truth table that will describe this behavior. We have our 2 inputs, A and B, and our output, Z. Now, given the 2 inputs, that's 2 to the 2 or 4 different combinations of inputs, 0, 0, 0, 1, 1, 0, 1, 1. And the behavior we are looking for is shown here. When A equals B, such as 0 and 0 or 1 and 1, our output Z will be equal to 1. And when A is not equal to B, say 0, 1 or 1, 0, our output Z will be equal to 0. This behavior then is described by an inverted XOR. We could construct an XOR using our abstraction shown here with an XOR in series with an inverter or a NOT logic gate. Here we have our 2 inputs, A and B, and our output, Z. This functionality then describes the digital comparator, the hardware, let's say, that will allow us to implement this functionality. A slightly more complex example then will be to compare a 4-bit digital word. In this case, let's compare A0, A1, A2, A3 with B0, B1, B2, B3. And we have then the building blocks from the preceding slide that will allow us to compare each bit independently. So implementing this functionality then, we can compare each bit to explore if they are equal. So I can compare A0 to B0, A1 to B1, A2 to B2, and A3 to B3. I can do a bitwise digital compare here. And in the case where I have a dual input logic gate, I'll need to compare the output of each XOR in series with the inverter. So I'll add an AND gate here that'll compare the output comparing A0 to B0 with A1 to B1. And I'll add a second AND gate here to compare the output comparing A2 to B2 and A3 to B3. I'll add one additional AND logic gate here to compare those 2 subsequent outputs, and that will allow me to describe my final output, Z. So Z will only be equal to 1 in the case where A0 equals B0, A1 equals B1, A2 equals B2, and A3 equals B3. We appreciate now that digital logic forms the basis of all computation, from your microcontroller to your cell phone all the way up to your laptop computer. So let's take a look then at addition using digital logic here. In this case, we'll do 1-bit addition. So we have two inputs, A and B. Let's say A is 0 and B is 0. We add them together. That'll give us 0. In the case where A is 0 and B is 1, we'll add those together to 1. 1 plus 0 is 1. And lastly, when A is 1 and B is 1, that gives us 2, which in binary will be 1, 0. Here, 0 will be the sum, and 1 will be the carry. When we create the truth table then to describe this functionality, we'll have to account for our two inputs, A and B, and the 2 to the 2 or 4 possible combinations, as well as the sum and the carry. So when our inputs A and B are 0 and 0, their sum will be 0, and the carry will be 0. When A is 0 and B is 1, that sums to 1, a sum of 1 and a carry of 0. Same thing for 1, 0. And in the case where A is 1 and B is 1, that sums to 2, so my sum will be 0 and I'll carry a 1. If we look at our outputs then, you'll notice that the sum output looks a lot like an XOR, while the carry output looks a lot like an AND. So if I were to sketch this circuit then, I'll need an XOR gate and an AND gate, and I'll need my two inputs A and B. The XOR gate will give me my sum output, while the AND gate will give me my carry output. Now this is what's known as a half adder. The half adder performs 1-bit addition using digital logic.